Hey, this is Horner, and this is Gravity and Coulombs Law, question F3. We have a student looking at a star, so here's the star, has a mass of capital M, and there's a gas cloud on the outside of mass M, and it is orbiting the star. So it has got a nearly spherical shape, and it can be treated as a single object. Notice that the direction is counterclockwise. So because it's counterclockwise, we know that that is going to be a positive direction. You'll have positive angular velocity. You will also then have a positive angular position change. So here our change in our angular position, which remember is a radian, is in that direction. So we're going to say that's a positive theta. Write expressions for the following in terms of big G, big M, little m, and capital R. So notice when I went through and did it, I left these as little r's to show you they wouldn't give you points for this. You absolutely positively have to make sure that all of your r's are capitalized. If they are not, they will not give you credit for this. I know it's crazy, but they ask for it that way, so that's why. They want us to find first the speed that the gas cloud orbits the star. We know the force of gravity between both is equal to this, and we know the centripetal force, which holds this in, okay, which is pulling the gas cloud in, is Fc is equal to m, little m, v squared over r. When we do this, we have Fg is equal to Fc, so we're going to set those two things together. Notice the little m's cancel, so we're not really worried about the mass of the little thing. When we do that, we get rid of them. We get v squared is equal to g big M over r, and so you solve for velocity. You get 2 points, one for setting these two things equal to each other after you've done this, and then 1 point for putting the final equation for velocity. The total energy of the kinetic star cloud system is what we have to find next, assuming that neither star nor the cloud rotate. So here we go. Kinetic energy is 1F mv squared. We plug in the equation for velocity that we had. So here's the v squared. It's going in here. And now we're going to do some just rearranging, and we get this. Now, remember, capital R's. So I'm going to go back and put in capital R's for everything since that's what it wants. We're now going to say the total energy here is the kinetic plus the potential. Our kinetic energy is big G, little m, big M over 2, capital R, and then that is minus big G, little m, big M over R. So this right here is the potential energy of the system. If you subtract the two, we need to make a common denominator. So I saved this so you can see me do it. In order to do this, I have to multiply both the top and the bottom by 2. Why is that? I need a common denominator. If I do that, I'm going to get, I've got to take the 2's here. 2 minus g is going to be negative g. 2m minus m is going to be negative m. And 2 big M minus m is going to be big M. Then on the bottom, I've got my 2r's. So you get 1 point for the kinetic energy equation and 1 point for the total energy. And that's how you end up getting it. The angular momentum is basically, remember, angular momentum is the moment of inertia of the system times the butt, which is the speed. And for I, we get m squared, mr squared, because it is a sphere. And then omega is equal to v over r. And that's because we know that v is equal to omega times r. We're going to plug these two things in. And when we do that, notice that 1r crosses off on the bottom and our squared crosses off, and we end up with mvr. Now we're going to plug in the speed that we had up top. So here's our speed again. It gets plugged in for the speed here. So we have m times r times the square root of g times m over r. And if I want to simplify this, which you don't have to do, but the answer key does say or, I can square everything when I do that, and then take the square root of both sides after crossing off one of the r's. I end up with this guy. That's part A. For part B, the student is making several observations over a particular period of time, and they notice that 1/2 of the mass of this thing goes into the star. So half of the mass here. So now this becomes m over 2, and this gets m over 2. But it's big M, so it doesn't pick up as much mass in a relationship or a ratio as this one is losing. It's losing half the mass. This is picking up a fraction of its mass. If the orbital speed of the remaining gas is it faster, slower, or the same, it will be faster. And that's because V, remember, is equal to the square root of gm over r. We solved that earlier. And our big M increased since the gas went into the star. So the gas that's going into the star makes this M bigger. And so speed doesn't depend on the little mass that's left. So if you want to, I would make this big M. That's for the mass of the star. And you might make this mg little g. Don't make it big G. It'll think that it's weight. That's the mass of the gas cloud. Does the mechanical energy of the system increase, decrease, or remain the same? So this one you're going to see I had to kind of use more space here. It should increase. The energy depends on the combined or the product masses. So in this case, when I take M, which is the gas cloud, and divide it by 2, and I add that to big M only slightly increases. So the product of the original masses is smaller than before. So let me give you a math example. If the mass of the gas cloud is 4 and the mass of the star is 10, when I multiply those two together, I get 40. But if I half the gas cloud and then add that other half to the mass of the star, that would be 4 over 2 plus 10 times 10 plus 4 over 2, which is 2. So there's 4 over 2 is 2. And then 10 plus 2 is going to be 12. That's only 24. So notice that the star doesn't pick up as much mass as this thing loses. So the total energy here is negative, and now is a smaller negative, so the total energy actually does increase. If the star wasn't rotating before the accretion event, so accretion is when that star picks up the mass of the gas cloud, is the star now rotating clockwise, counterclockwise, or not rotating? It is going to rotate counterclockwise. And it's because if you saw as that gas cloud went into the star, so here's the star, as that gas cloud went in, the angular momentum decreased. So the m squared times m decreases if your m over 2 and your m increases slightly. So that gas cloud lost angular momentum in that counterclockwise direction. So this gas cloud lost in this direction, so now the star's got to pick it up in the same direction. That is the law of conservation of angular momentum. That star picks up the counterclockwise momentum in order to conserve, so it's got to start rotating in that direction. And that is the end of F3.